Hello, everybody, and welcome to our webinar on building fast data loops from insert to query response in ClickHouse. My name is Robert Hodges, and I'm joined today by Diego Nieto, as well as Chiara Tosselli. Um, so before I dive in and do some more detailed introductions, um, let me give you a little bit of housekeeping information on this. First of all, this meeting is being recorded, as you may have just heard, so you don't have to frantically scribble notes. What will happen is we will distribute an email message with a link to the recording as well as the slides. So anything you see in the slides, you can go ahead and you'll get copies that you can cut and paste from. Um, Another thing is we do have the opportunity for questions here. I don't think this webinar is going to be super long. This topic is actually somewhat experimental for us. And so there may be a little bit more give and take in this one. We'd love to hear your comments and questions about the problem that we're exploring here. So anyway, if you do have questions along the way, type them preferably into the Q&A box. My colleague Diego can answer them. We'll also review them directly after at the end of the call if they're for some of the more interesting ones. And we don't really care. You can also put them in chat. We'll see them there as well. So with that, I'd like to dive in and let's do a little bit of introductions here. So I'm Robert Hodges again. So I've been working on databases actually for 40 years, but it makes me sound kind of old. On Kubernetes since 2018, open source databases since 2006. My day job is I'm CEO of Altinity, but I'm basically a database geek. Diego, do you want to just give a quick introduction of your background if you unmute? Tell
Yeah.
people a little bit about yourself.
Hello. Hello. My name is Diego. I'm software engineer working at support. And basically, I also like Robert, dealing with databases a lot, Postgres, ClickHouse, and many others. And yeah, I like also Python and Rust. I do some stuff in there.
So the mine are Golang and Java. So great. And just a little bit about Altinity. So we are an enterprise provider for ClickHouse databases. We operate a cloud. It's called Altinity.cloud. It runs in Amazon, it runs in GCP, it runs in Azure. And as of about a week ago, it runs in Hetzner. If you are Hetzner users, famous for low-cost computing. So it's a very flexible. It can run in our account, or there's also a way to set it up a BYOC so that it runs in your account. We have a bunch of customers using it both ways. We are also the authors of the Altinity Kubernetes operator for ClickHouse, which at least some of you on this call are likely using. It's the most popular way to run ClickHouse on Kubernetes. We also maintain ClickHouse Backup, the community Grafana provider, and a number of other open source projects. We're really big into open source. That's enough about us. Let's jump in and get to the topic at hand. So, which is ClickHouse. And for those of you that do not know it, ClickHouse is a real-time analytic database. The way I like to explain it is it's kind of like a mix of a database like MySQL, which is open source, runs practically anywhere, speaks SQL, and a, a traditional data warehouse like Vertica, which some of you may have used in previous years, which means that it originally had a shared nothing architecture where there's a bunch of nodes on a network with storage, stores the data in columns with high levels of compression, can do parallel execution across a bunch of nodes, can do vectorized execution, which means that as it's processing the columns, it breaks them up into little pieces and pushes them onto the excuse me, pushes them onto the processor and uses as much as possible single instruction, multiple data uh, uh, commands to rip through the data as quickly as possible. It scales to many petabytes. There's a system that we're working on with some in one of our engagements that they're dealing with 11 petabytes of compressed data. There are systems larger than that. In fact, many of them on ClickHouse. And of course, ClickHouse, unlike the data warehouses of yore, is open source. It's Apache 2.0, and in this, it of course shares the um, shares this with many other databases like MySQL, like Postgres, um, and DuckDB, so on and so forth. So because of all these properties, this has made ClickHouse incredibly popular. It is the most popular engine for low latency or real-time analytics. By that, we mean things where you have high levels of ingest. People want to react to the data quickly. They want to get answers quickly from the uh, from the data and basically get insight on business problems in a hurry. So let's talk about that. So the goal in this presentation was to talk about fast data loops. And this is sort of a name that I made up when I was doing the topic of the talk. We'd love to find a different one or a better one that is speaks to you. But the basic idea here is that many systems that use ClickHouse are trying to react quickly to external events. A classic example of this is what's called SIEM, or Security Information and Event Management, where you have a system, often multi-tenant, that is scanning a bunch of data from a bunch of different sources, and it is looking for problems with security. So it's looking for violations of policies, it's looking for attempts to break into systems, it's looking for things that are just questionable, maybe maybe somebody's accessing S3 in an unexpected way. These systems try and collect information. They feed it into tables in the database. And what we want to do is generate alerts or notifications to users that they can respond to and then investigate further. So this is a very, very common pattern in many use cases. And this picture basically shows how it works. So we have ClickHouse in the center. And so we're going to talk about how to read data in quickly. We're going to talk about how to generate alerts, give you some ways of doing that. We're also going to talk a little bit about managing the alert data, sort of the state of an alert, and and um, and hopefully this will be helpful as you build these systems yourself. So let's start on the first problem, which is inserting data quickly. So for those of you who have used ClickHouse, you know that it has incredible capacity for absorbing data. It's possible to even, just as a test, to generate tens of millions of rows per second and have them inserted into ClickHouse. I did a demo a few years ago where I was generating 1 trillion lines of data, and I was able to generate from system.numbers 80 rows per second, or 80 million rows per second. It's really, really fast. So when you're running an application in ClickHouse, you're first of all going to think of some table that you're creating. And in this particular case, most of the examples we're going to use are built around a table called test, which is just temperature measurements. It's based on a blog article that we did many years ago about dealing with trillion row data sets on an Intel NUC, or actually not trillion rows, I think it was billions of rows. But basically what it's doing is it's measuring temperatures. They come from sensors. The sensors have types. There's a time when the measurement is taken. There's the actual temperature itself, and then other measures coming from the device, measurements coming from the device, or events, like, hey, it's restarting, or it got an error, so on and so forth. It's put in merge tree, which is the workhorse table for ClickHouse used for big data. And then we partition it, as is common in most large data sets. They're partitioned by time, so that the table is divided up into, that is to say, the table is divided up into chunks. And in this particular case, all the data from for a particular month will reside in the same chunk or partition in the table. And within that partition, if you go and look inside it, you may see the data, if there's enough of it, divided up into a number of parts, which are just additional subchunks, if you will, of data under that partition key. And then finally, it's ordered. So in this case, by message type, sensor ID, and finally time. This ordering ensures that, for example, our queries run quickly, that we get good rates of compression, so on and so forth. So much for data design. Let's talk about getting data into it quickly. So the simplest way of putting data into ClickHouse really quickly is big batches. And by big, we mean really big. So the default block size for ClickHouse is over 1 million rows. but you can extend that. So you can, there's nothing wrong that with putting, say, 50 million rows in at a time, if that's how fast. If you're getting 50 million rows of data in a second, you can put it into ClickHouse that fast. All you have to do is have enough memory so that when those blocks come in, when you're doing an insert, ClickHouse can build the parts, that is to say, the blocks that it's actually going to write to storage. It builds them, it sorts them, and then it flushes them out to disk. So if your application already does this, actually you're in good shape. You may not need additional tricks. And the commands to do this are very simple. This is an example where we're using a curl command to post data through the um, HTML interface, uh, and you will and basically it's just inserting a bunch of CSV. In this particular case, the CSV file is just piped into the curl command, so it's just blasted up using the HTTP format and using this simple insert command. You can use this to insert, say, 50 million rows if that's what you want to do. It's quite simple, but not everybody has an application that's set up like this. So there's a couple cases where fast insert becomes a problem. The most common case is that it turns out, and this is true in security information and event management, that you actually have many sources of data. So you may have hundreds or thousands or tens of thousands of machines that are generating relevant log information that you want to be scanning. And all those services are can be treated in, superficially. You can just consider them to be clients, and they could all try to log their data directly to ClickHouse. So as a result, they're going to have small inserts, many small inserts coming from a lot of different locations. And that's a problem that we're going to focus on because ClickHouse has a number of good ways of solving this problem. There is another class of insertion problem that you can run into, which is you have extremely large inserts from clients. And in this particular case, if the files are quite large, it may be problematic to break them up and to funnel them efficiently to ClickHouse. We're not going to talk about that particular problem very much in this talk. I will just say that the simplest way to do that is to push those files to S3 and then read it directly using the S3 function or S3 cluster function. So ClickHouse is very good for reading data of S3. We've touched that on that on previous webinars, and we'll do so again in the future. So let's get to the problem of small insert from many clients. Well, the number one way to handle this is something called async inserts. And basically what an async insert does, this is a simple example of, oops, the table name is incorrect. It should be test. Um, you have an insert into our table test, and here's the values. We're just doing this as a SQL statement. And what will happen is that when async inserts are enabled, we will automatically write the data into a buffer. And then, provided the client asks for it, we will hold the client connection and then notify them when it actually commits, when it actually goes to storage. So what you can do with this is you can have a bunch of people executing this command simultaneously, and they will, they will see you know, basically they'll see their application kind of pause, and then when the data is actually accepted, because it's basically going to be collected together and then pushed into table test in a big batch, the client gets acknowledgement back. So I want to introduce here the knowledge base. There's a knowledge base set of articles on this about async inserts. This is the link right here. So how do you enable async inserts? Because they don't happen automatically. Well, there are a number of properties that you can set. And one of the things you can do is actually set them on the insert statement itself. If you just say insert so-and-so settings, and then just as it's shown in this syntax here, you can then set these properties, and that will enable async inserts. However, that's kind of a painful way to do it because it means you have to go change all your code and all your insert statements that have to do this consistently. What is much simpler to do is actually to create a user for this and give it a settings profile. So in this screen, what I'm doing is, and this is something that Diego has uh, does quite a bit and had documented in the KB. We're going to create this user async, but we're first going to set up an async profile, and the settings are exactly the ones that are required for async insert. The first one turns it on. The second one says, hey, when you send something, when you post something out, wait for it to get processed so that the application will know if it fails. The third thing is to say how long to wait. There's a number of properties that you can set. This one says basically don't wait 10 seconds for this thing to go in, or any number you want. And then finally, and this is really important, there's a new setting. If you use async inserts, there's a new setting in ClickHouse, I think as of like 24.3 something.
24.3, yeah.
Thank
They
you.
included
Yes,
that.
thank you. I thought that's what it was. So as of 24.3, there is this somewhat pernicious setting, um, because with 24.3, ClickHouse introduced adaptive async insert, where it actually figures out based on your data what's a reasonable level of buffering. But if you fail to turn that off, then what will happen is it'll ignore your other settings. So this is an important setting to, if you want to set these explicitly and not use adaptive async insert, you want to turn it off. And so you put these in, create a user, and then use that user to do your updates. It's as simple as that. And this is for those of you who tried async inserts before. Back in 2023, they had a reputation for being somewhat unstable. That's not true anymore. There've been a lot of the issues have been fixed. It's a very capable feature.
Yeah. And also it has a lot of observability with a lot of tables, and you can check
Yeah.
them in query log, in asynchronous insert log. Yeah, so it's nice.
Yeah.
Yeah.
And this is something that these are two tables. If you use asynchronous inserts, you should know about these two system tables. Generally speaking, if you've ever heard any of my the webinars that I've done with either by myself or with other people, I love ClickHouse system tables. They're really awesome. And so async inserts have this great observability, as Diego says, where they have, if you're doing async inserts, um, while the insert is waiting, it will appear in the asynchronous inserts table. Once it's no longer pending and has actually been inserted into the database, it'll go into the log. So you want to ensure that that log table is enabled, and then build your observability so that you can track, for example, how many pending async inserts do you have at any given time, and also be able to track how many you have over time. So these are super useful, and like all the system tables, very accessible, easy to understand. Let's talk about an older way to handle small inserts, and that is buffer tables. I bring these up. We don't recommend them because async inserts have gotten pretty good, but people still know about them. Sometimes they can be useful. Um, Let me show you by creating a buffer table. So it basically sits in front of the table you're actually updating, and it does exactly what the name implies. It buffers the inserts in memory. So this creates a buffer table. It uses the buffer engine that as test, the create table test buffer as test says, hey, take the column definitions from test so I don't have to repeat them. And then there's a bunch of properties here. So the database and table that we're buffering, how many independent buffers to use so that you can have a bunch of things running in in parallel, and then a number of parameters basically saying, hey, you know, hold for at least 5 seconds, but no longer than 30, hold for at least 1,000 rows or no more than 1,000,000, so on and so forth, and same thing with number of bytes. So these basically give the parameters for when to flush, and then when you do the insert into test buffer, which should say values, by the way, these were actually real examples, but somehow didn't get cut and pasted or copy pasted in right. So you insert in, what it's going to do is actually push it into the buffer table. And I think we have a picture. So here we insert in, and there's the data. And what happens is it appears in memory. And what's kind of interesting about this is it will take some time to get forwarded to the test table, but you can do selects off the buffer test, off this buffer test table, and you'll see all the data. So it will basically show you the data that it has buffered, but also the underlying data. So you can run, you can actually run selects on it to see what's going on. There are some downsides to this. So buffer tables have some kind of some corner cases. Diego, if I recall correctly, like around sorting and things like that. There are cases
Mhm.
where it can behave strangely. The biggest problem, though, is that if your database fails or you have some other problem, this is an in-memory table, and your data will be
Yeah,
lost with no act to the
yeah.
application.
This is like
So
having wait for async insert equals 0.
yes, exactly. Yes,
Yeah,
exactly. So don't,
for
yeah,
the
just put some data in. You really don't care whether it gets in or
yeah.
not.
Mhm.
So this can be this can be a real problem. And so as a result, the async inserts have the same problem in the sense that if ClickHouse crashes, you're going to lose your data, but at least your applications will get some they're held and they'll see the connection fail,
Yeah.
and then they can insert it again.
The retry, it's durable, the wait for
Yeah,
async insert property.
yeah,
But
yeah,
if I don't want to sound reckless here, but where they shine, I guess. I mean, I saw that it's when you disable durability
yeah,
and you just have like 1,000 insert in a second, and they will all be squashed and they will form a block. And
yeah,
yeah, but the problem is if it fails, you will lose data. But clients won't be blocked. I mean, because wait for async insert, what it does, it's blocking the client until the
yeah.
flash time. So you would see, like if you're using Python or Rust or whatever, that the client is blocked unless you use Asyncio or any other
Right.
asynchronous framework. Mhm.
Yeah. And to be clear, much of the data that actually flows into ClickHouse, for example, monitoring data, if you lose a few seconds, who cares? Because they're often monotonically increasing counters, um, or they're things where, hey, if you lose 2 seconds, it doesn't matter. Now, if you lost a few
Yeah.
hours, that would be a problem because you wouldn't be able to figure out, you'd lose visibility into the system, but that's not a big deal. So this is a good point, though, to talk about, hey, what if you actually did care about the data? How would you solve this problem? Um, well, Kafka, in a word. So what Kafka does, Kafka is, I think most people on the call probably know about this. It's basically an event queue or a message queue on steroids. And Kafka is basically a distributed log. That's fundamentally what Kafka servers are. And they have these things called topics, which are basically queues. And the cool thing about Kafka is you have on the left side, you have what are called producers. On the right side, you have the thing reading out of it, which is called a consumer. And in this case, what will happen is if the producers, say generating these temperature readings, push the data into Kafka, it all gets buffered up in durable records in Kafka, which then can be read in big chunks by ClickHouse. So it really helps us solve this problem of being able to handle data. So let's look at some example code to set this up. So one of the simplest and fastest ways to do this is to use something called a Kafka table engine. So this is a table engine that's built into ClickHouse, and what it does is it basically takes a topic from Kafka, and it basically puts a wrapper around it so it looks like a SQL table. And so when you do a select off it, you are effectively reading from the topic. So the topic has your messages. You configure the Kafka table engine to point to it. It will consume the messages. And then the next thing you do is you could select them yourself, but that wouldn't be very useful. What you really want to do is put these in a table. So the simplest way to do this is to set up what's called a materialized view. And materialized views, if you're not familiar with them, are like triggers that automatically fire whenever data is inserted into the table that they're based on. The insert occurs, the materialized view will cause a query to run automatically on that data. So any select query you want, and then the results of it will be put in a target table. In this case, a merge tree table. So, but it can be anything. And so what this chain does, this little pipeline does, is something arrives in Kafka, materialize view fires, and then the result gets put in merge tree. So let's see how this works in practice. So this is an example of setting up a Kafka table engine, which is, or a Kafka table, which is going to accept data. And in this particular case, it's configured. So we use the engine Kafka, and then the settings just give us the information about, hey, what topic to read, for example. That's the topic list. Where are the brokers that we read from? And most importantly, well, well, very importantly, is what kind of data we're actually reading. So you have to give Kafka a clue. In this case, it's a CSV with column headings.
Yeah.
And so that reads it in. There's a bunch of default parameters about how often to pull. And then here's a materialized view, which will select the data and push it into the test table. There it is right there. And so it simply pulls that data out, which is automatically converted by ClickHouse from CSV format. And it's the results, every time this fire, the result of it goes into the test table. Diego, were you going to say something? I heard you.
No, yeah, that I mean the Kafka format is important, and ClickHouse will use the inference
Yes.
mechanism to get the types and set the types.
Yeah.
If they are nullable, just with some parameters like input format default as null, it will just
Right.
read and write the defaults instead of nulls. It will do a lot of stuff in the background.
Right. Yeah, and actually the formats have gotten the treatment of formats is something that's gotten really good with ClickHouse over the last few years. So for example, if you're reading Parquet, it can map them to nullable columns and things like that. So these are all things that have really improved. So here's this is how it works. And then here's an interesting topic is like with Kafka, one of the problems you have is that if this conversion to CSV fails, then you get an error that just pops up in the log and it actually then just keeps trying to reread it. So what we'd really like to do is let stuff fail and put it in another queue. So there is a way to do that. And this is something that comes, again, kind of a nice example that comes out of the KB. Um, you can create a materialized view that specifically looks for Kafka errors. So in this case, and what it's going to do is it's going to give the topic, it's going to give this is the table, and the partition is read from the offset. The actual thing that it read, this is this is basically like a dead letter queue, and then the error that it got. This is what's going to be in your table, and this select statement is how to read it. So Kafka has these things called virtual columns, like topic is the name of the topic it read from, and you can see that what this is doing is it is selecting things where the error message is greater than 0. So it's basically trying to read off the topic and find things that couldn't convert. And they'll pop in there and then you can look at them and figure out what's going on. So when you put this together, if you take something that's coming in, what's happening under the covers, it's written to the Kafka topic. The test Kafka table is reading that topic. And then if it's successful, it will go ahead and get put into this test Kafka materialized view, and or the test Kafka materialized view will fire at the if it's successful, it will go into merge tree, and then this Kafka errors, which actually underneath should be yes, it's a merge tree engine. It just contains all the things that failed. So this is your basic pipeline. It bifurcates based on whether it's successful or not. So this is pretty flexible. So let's see. So that's Kafka. What if that's not good enough? And well, one of the ways that it might not be good is that in this picture, the Kafka table engine doesn't know about once and only once semantics, or it does a pretty good job, but it, the basic the default semantics are at least once, so you can get duplicates and you can get case, and this will happen. It doesn't happen very often. Things have to change in the system. So for example, Kafka can rebalance topics. which will cause different consumers to reread stuff. So that's an example of where you can get extra data. There are other corner cases. If you want to avoid those problems, you can write your own application. So if we're using librd Kafka, or if it's in C++, or whatever library you want to use, you could build Kafka has this sort of connect framework for building consumers and producers. And the libraries have transactional semantics. So in that particular case, you would build your own consumer in your favorite language. Virtually every common language is supported, and uh, you would use that to read from Kafka and apply to the table test. You can also put additional logic to do syntax checking, or to deal with errors, like protocol errors, things like that. Also generate alerts. That's another reason why you might want to do this. But that's a good thing to do. There is also the project called ClickHouse Kafka Connect. It's a ClickHouse Incorporated project. It is an external connector which just reads from Kafka and puts it into ClickHouse. So that's another one you can try. I've looked around, I didn't see too many other projects, but I would say right now, most of the people we know are writing their own consumer, because they're actually, for specific use cases, they're really not that hard to write. So people just do them, generate a container, and then run them.
Yeah, if I
So
may add
yeah,
something, Robert, I hear yeah, for me, Kafka Connect just adds complexity, and to get exactly one semantics, yeah, writing the consumer, it's the best way to go. But since 24.8, you can get exactly one semantics. Is it still experimental or beta? I don't remember. And basically, to get this exactly one semantics, you use the keeper.
yeah,
And you store and you manage the offsets in Keeper. I mean,
yeah.
there is a PR we can share later if you want, and you will get, using the Kafka engine, exactly one semantics using Keeper as a storage.
Right. And you'll notice here that this picture here doesn't show any coordination with Keeper. Um, because the big problem you have is just remembering what you read. So you'll know that, like, if a topic gets rebalanced or if you crash, to make sure that you have the right restart point on the topic. So yeah, that's a feature that was asked for a long time. I think it's still experimental, but that's definitely something to look at. Okay, I think that's about it for handling lots of inserts. Let's talk about generating alerts and a few tricks to do this. There are a number of ways to do this outside of ClickHouse, which we won't really talk about, although it might be a good topic for a later time. Something like Flink, for example, can process the events coming out of Kafka and generate alerts to let people know, hey, there's something here that you should be looking at. Maybe go to the database and find it. Um, so if you're just building an application and uh, to generate alerts, there is a simple answer, and that's just, hey, go poll for it. This is a terrible way to do it. Select star you never do on data warehouses, but if you had a small number of things you're expecting to come back, you could have just look for any reading where the temperature is above 90. So that is, and that's the way some applications do it. But it's pretty quick as soon as you get to larger data sets. This is whatever you're selecting for is likely to be expensive to do, especially if the table is large. So one of the things you might want to do just to speed this process, just to speed polling up, is to use a materialized view so that we start to see outliers more easily, because that's typically what you're alerting on. So here's an example where we're just looking for the min and max temperatures to find hours where there was a max temperature, to see what the max temperature was for the hour and the min temperature was for the hour. That table is going to be a lot faster to scan than looking at the actual data. So this first thing creates the table using aggregating merge tree, which is uh, basically going to store these. And simple function is a complicated way of store the max value you've seen. Or the min temperature, the max temperature, this is a definition, partition it by hour, order it by hour. That's going to basically be your aggregation key. And then in the materialize or your group by key, and then the materialized view just operates on, let's see, here we go, as select from test. So the so whenever test is anything arrives in test, we're going to run this query and we're going to put the results into test outliers. So this is pretty simple, and it's still supporting polling, but it speeds things up. However, there's another thing we can do which might be more interesting, and that's to really remember the outliers somewhere. So we don't actually have to go pull for them. We just have a table where they're already existing. And here's an example of you've got a test. We're going to create a table that's going to hold the outlier values, and so we call test outliers 2. It's merge tree. Um, has partitioning by month. So it's going to capture all the outliers for the month and in each partition. And the materialized view for this is very simple. So any temperature that's greater than 90, we're going to go stick it in this table. So you can see all of those outliers very, very quickly in this way. Of course, the things you might be selecting on might be much more expensive. This particular query is probably one you could just run on the data set yourself without but if you do this regularly, this is much simpler, and you don't actually you scan a lot less data. So, but we can do one better. We can remember outliers. We could actually tell somebody actively, because here somebody's still going to need to poll. Let's try and actually send a message to somebody. And here's a great way to do it. Oh, by the way, so here's the before we do that, here's a picture of what happened. Where let's say that we're inserting into the test buffer because we were using a buffer table. It's going to arrive in table test. The materialized view is going to fire, and it's going to hit the test outliers 2 table. All the ones that are out of bounds will get captured there. So this is pretty simple. We just go to that table and look at it. So now we can get to telling somebody about it. So, and for that, we can use the URL engine, or URL engine, which is basically allows you to do gets and posts on data in or to a web server. So any HTTP endpoint. And in this case, we're going to create a table which is going to have our data types, going to give the engine. And this actually is a little bit like the way the Kafka table engine is structured, only in this case, we say URL, we give the endpoint. So this is where to send the data, what format we want it in. We're just going to send it as CSV. And then we'll create a materialized view, which whenever something arrives in test where the temperature is greater than 90, we're going to send a CSV record to this website, which is, as you can see, just running on the local host, but it could be anywhere. And it could be HTTPS. It's pretty tolerant as long as it has certificates. So what does that look like? Well, basically like this. So we insert into the test buffer. So assuming we have a buffer table, it's going into test. The materialized view fires. And in this case, what it's now going to do is send an HTTP post with chunk transfer encoding. This is actually kind of important because if you just have a simple, what you could do is build a very simple client that just reads posts. But in fact, you have to support this, what's called chunk transfer encoding, which means that instead of receiving the data as a single blob of data, it actually can be split up into a bunch of chunks that are sent in parallel. So it's an optimization on HTTP protocol. And so you just support that inside your um, uh, inside your server. Any like web servers support it by default, but your application will just need to do this, and you'll need to collect the data correctly. But that will then give you a notification. And actually, if you set up the server, and I have an example of it, which I'll share the link. What you'll then see is every time this materialized view fires, you'll see at least one message in your log where it's actually receiving data. So So this is a good way if you want to do sort of like a webhook type approach to getting alerts, and then this could be connected to an application that does something about them, maybe puts them somewhere else. Um, However, we can also use Kafka. We can use Kafka to get stuff in, and we can use Kafka to put it out. Here's an example of what we're doing is we're using Kafka to actually receive the data, look for outliers, and then post them back out to Kafka. So this is a little more complicated. Um, let's actually flip forward um, and show a picture of it because I think that makes it easier to understand the sample. Here's a temperature, a reading that's exceeding is out of bounds for us. What we're going to do is read it in using a Kafka table engine table called Kafka Consumer. Actually, I've shortened the names a bit so they fit in the boxes. But the consumer gets it. There's a materialized view that's reading off it. It's going to take the values and put them in temp alerts, anything that's interesting that we want to alert on. There's going to be a Kafka producer table, which is to send stuff out to a queue that holds alerts or a topic that holds alerts, and somebody will read it and do something about it. And then connecting those two is the Kafka producer materialized view. So anytime something shows up in temp alerts, the materialized view will fire, and it's going to select the data into the Kafka table, and that will send one or more messages. Let's look at the code that does this. This was, by the way, thank you, Diego, for putting this together. So here we go. The names are a little bit longer here. I shortened them to make them fit in the box, but here we go, the full names. So here's the consumer. So just like the previous example you saw, reading off Kafka, a materialized view. Now, this time, what we're doing is looking for stuff that needs to be, that needs to be picked off and where you want to generate an alert. So that's the materialized view that does that. Then here's the intermediate table that those alerts are going to. They're very simple in this case. We store time, temperature, and alert level. It's like, hey, there's something happening here. You ought to go do something about it. And then we push the data. Um, this is that's a great table. So this is our producer. So a Kafka table where it's going to go to. And then finally, here's the materialized view, which is going to actually select the data into Kafka. And what you can see here, this is a great example where you can now add any kind of logic you want in this query to to reshape the data so that it generates the best possible alert. And so I think this is a really nice example, like using this multi-if where you can show the ranges of like, hey, like the critical one, the boiler is about to blow up. Um, you can then feed that into the alert and hopefully somebody will pay attention to it. So in this case, we're not really using ClickHouse to store data very much because the alerts are really just there. Sort of it's only a small fraction of the data that's actually getting stored, and Kafka is basically acting as a pipeline to process things coming out of Kafka. So a cool example. And again, so there's the picture of what happens under the covers. So with that, those are some basic tricks for getting alerts to happen. There's a final topic, which is how to manage the state relating to alerts. And this is kind of there's a number of ways that you can do this, but what we see commonly is a couple of approaches, but one of the most common ones is to use the replacing merge tree. Sorry about that. Let me correct this immediately. Placing this was, there we go. Can't have bad data in our slides. There we go. Replacing merge tree. So I'll show you how replacing merge tree works, but basically it's a table type that allows you to change the data by doing inserts. And that's always a good thing when you have very large data sets because actually updating rows, as you may know from using things like alter table update or alter table delete or using so-called lightweight deletes can actually be very expensive in large tables, particularly for observability data sets like this. So this is creating the same table that we have for, except there's a couple of new bits of information. So I've basically taken that previous example that that Diego helped set up. And I've added, first of all, an alert ID, which we're going to assume we're going to generate it somehow. And I'm going to add some additional fields: acknowledged, effective date, and then this field called is deleted. So the idea is the alert ID, um, gives us a number so that we can go check and test whether this alert has been dealt with. We can find it again. Acknowledged is 0 if it has not been acknowledged, and a 1 if it has been. And then the is deleted field, we'll see how that works in just a second. And then the effective date is just something that we use to track the progress of the changes to the table. So replacing merge tree is this engine, and what you have to do is give it, this is called a versioning. This effective date is used for versioning the data. So as the values increase, those are the versions that determines your current version. Is deleted is just a flag that says whether the table is whether the row is deleted or not. We still have to partition, and then there's a really important point. You have to order by. The order by in replacing merge tree is what determines the how to collapse basically how to deduplicate the rows. So anything that has the same alert ID will be treated as the same row, and the latest version will take precedence. How does that work? Well, a picture helps. This is basically essentially that table where we have effective date, which is used to create our version. And so as rows arrive, version 0 will be the first one. That's when you do the first insert. Later on, you might change the value. In this case, you will go ahead and update it. In this, you'll notice the alert ID stays the same. It's the key. And then when you finally decide that you want to delete it, you'll put a 1 in the is deleted column, and then that will cause the row to disappear. So how do you get it to disappear? Well, that's something that has to get resolved at read time. And let me show you how that works. So here's how we add an alert into the table. So we go ahead and give the 4 fields. Most of the rest of them will default. We add this in, and then if we do a select off it, we will see that the alert, we'll see all the data and we'll see acknowledged 0, because it's actually it defaults to that when you first put it in. Notice this important setting though: settings final equals 1. So you have to do what's called a select final in order to read this this data. So this 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 but there's only one row, so there's nothing to be deduplicated, and we get the row back. Let's add another row. So let's say we act this. So we acknowledge the alert. So we're now going to put it in and see here, we're adding the acknowledged column. We're setting it to 1. We're inserting the row. And then when we do this select star to show the settings with settings final equal 1, it will then automatically resolve in the later row takes precedence. So the one with the higher, in this case, with the higher effective date. And that's basically how it works. This is a very common pattern that we've seen used in a lot of systems. There are other ways to track alert state. Another way that you can do it inside ClickHouse is to use what's called the last point query. We're going to talk about, so a question popped up about, I'll get to that latest question that popped up in just a second. So so you can use a last point query. That is a type of query or type of materialized view that basically stores the most recent value for a particular key. I don't give an example here, but they're fairly there's something called argmax, which is there's a little helper functions that you can use in your materialized view that will store the latest value, for example, of a temperature or something like that. Another thing is actually to put it in a stateful database. So you could actually, for example, use that webhook alerting that we showed earlier, and you could go stick it in MySQL and just manage it all there. Another thing that you could do is ClickHouse has embedded RocksDB, so you could insert it in there. That's that's a more like basically a key value store. And the problem is though that it's not replicated. So that would be an issue if you lost it. And then finally, you could just use an entirely separate application. So there's plenty of ways to do this, but ClickHouse does give you good ways to do it inside the system, and a lot of people prefer that because it's just one thing to manage. There's a great question here. Diego, does replacing merge tree degrade the reading query performance a lot compared to regular merge tree?
I was answering the other one about Kafka, but I think I can do both. Okay, let's start then by the replacing merge tree. Does using replacing merge tree degrade the reading performance a lot comparing to regular merge tree? No, I mean, the only performance issue you will have with replacing merge tree is when you want to deduplicate. This is
Yeah.
what this engine is for. I mean, imagine that you have duplicates, you would use the final clause in the select, so the data will be deduplicated. Well, I mean, data will be read, and those duplicates will be deduplicated in memory. This is where
Ye-
the performance hits, but
ye-
yeah,
Yeah,
but
and
not
it's
in
really
reading the data. Yeah.
not in, the really important part though is when you're doing the deduplication is to and I've actually played around with this so that they end up landing in the same partition. If the changes land in different partitions, that is very expensive because you actually have to read the entire, potentially a very large part of the table to decide whether something needs to be deduplicated. There is a setting that says, "Hey, I can, uh, you know, basically by choosing your this key right here. Let's get this this order by." You want to choose this in such a way that
Mm.
you're assured that it always lands in the same partition. As it happens, because this time doesn't get changed, we just keep sending back the alert time. They should always land in the same partition, and they will resolve quickly. Um, but if you don't do that, it could be very slow. So anyway, so that's a great question and one that comes up commonly. And with that, actually, we're
Mhm.
getting to the end. So wrapping up, okay, first of all, if you like learning about ClickHouse, I just want to put a plug in here. We have a Altinity admin training starting next week, and we go deep on, you think you know ClickHouse administration. This, by the time you get done with this, you'll really know it. You also learn a lot about ClickHouse queries as well. And there's a bunch of additional places where you can get knowledge. I've uh, given citations to the Altinity knowledge base. This is just notes that we have whenever we answer support cases, that so we don't have to keep repeating ourselves. It's basically, sort of the raw notes. We do clean them up a bit from time to time, but this is a great place to get actual, uh, sort of information about particular things. For example, the RBAC article I cited here gives you examples how to do profile settings and things like that. The Altinity blog, which has articles on this, the replacing merge tree, there's a very good one called The Good, the Bad, and the Ugly. You can go read the ClickHouse code and ClickHouse docs. The ClickHouse docs are really good for seeing the overall um, state of so the overall syntax. What you may find where you want to combine them with something like the knowledge base is when you get to something like async inserts, where there's actually these property settings that can interact in kind of um, unexpected ways. The KB then gives you the details on that, things that are not typically in the actual underlying docs. And with that, we're done. I think you had one, Diego. You had one um, that you
Yeah,
did answered live. Maybe you want to talk a little bit about that, the bifurcation of errors. That's a great
yeah.
question.
Uh, well, if you saw the question, it's a nice one. Yeah, why this Kafka stream error mode? It's working nicely. It's mainly for parsing errors. I mean, if you have malformed messages in the Kafka topic, because there has been some problem, uh, what happens if you have this setting enabled, and Kafka will enable these virtual columns. And if there is a parsing error, if you wouldn't have this approach of handling error mode, you wouldn't see these messages in the main table. They won't be ingested because they were errorly. I mean, they were not parsed. There was error in the parsing. And you would say, where are these messages? I mean, I'm losing messages. Where are they? So they are not going to be in the main table. So that's not very convenient. You may check the log if you enable the Kafka debug logging, which is very, very verbose, I would say. You would see those. But this is very convenient because you can set up that materialized view, enable this Kafka error message parsing, and then if those columns are written, then there has been a parsing error, and those columns will be populated, and you can select on based on those columns and push the data to the Kafka error table. To be honest, few times you got parsing errors. This was like a long time ago. And right now, if there are, let's say, some parsing errors or some data mismatch or type mismatch, I mean, you're expecting a U64 and you got like a float and something like that. ClickHouse, because of this inference mechanism in latest versions, it can deal with all of that. It can substitute nulls for zeros if it's a number. It can substitute nulls for empty strings. It
Yeah.
can do some basic transformations, and you wouldn't even notice it. So all these, let's say, parsing errors are already more or less gone. I mean, but if you have like a JSON, for example, and you are missing the square brackets of one key, that is a parsing error, and those type of messages you would see in the dead letter queue.
Yeah, that one's a total lifesaver. And I know that because we also get binary formats like protobuf, for example,
Yeah,
is pretty pretty killer as
yeah.
something that can generate stuff that you simply can't read, and without somehow trapping the data that you're trying to read, it's really hard to debug what's going on. Um, Speaking of debugging and seeing what's going on, I see we're at 58 minutes after. Let's see, do we have any additional questions here? I don't see any. So what I
Oh,
think is we'll go ahead and finish. First of all, I'd like to thank Diego for helping to put this together. Thanks so much, Diego. I love doing webinars with you and
thank
on
you,
these
Robert.
topics. Thank you for everybody listening. Kira is our head of marketing and help organize this. One request, if you're interested in this topic, tell us. Oh, looks like we've got okay, no, I was saying, reading a question. Tell us about this, how you're building systems that require this kind of real-time response. If there are things you'd like to see in this talk, we're going to do another pass on this and basically build this out to give you the bag of tricks that you really should be looking at to build something like an SIEM application or anything else that wants to respond in real time to stuff in the outside world. So please forward those. You can come to and visit us on our Slack, talk to us, or you can get us on, we're both on LinkedIn. Any way that you want to, just contact us and tell us what you'd like to see. So with that, I'm going to end this. Thank you all very much and have a great day.
Yeah, thank you, guys. Bye bye.
Bye.